Good afternoon. I am John Borrego, Senior Vice President of Aerospace and Defense at Machina Labs. Today's discussion is simple. The industrial complex that supports our warfighters' challenge is not only a problem of capacity, but agility. If we want deterrence, we need factories that can switch from products quickly, not single-use lines that take months to retool. This presentation will walk us through the opportunities of how software-defined manufacturing can change the game. So pretty much everyone at this conference within the defense industry all agree on the same conclusion. We are not industrial ready for a major conflict. The gap is capacity, agility, and lead time for strategic weapons. Production cycles are too slow, and we are constrained by materials and skilled labor shortages. Backlogs are measured in 5 to 10 years, should be setting off the alarms for those who are not concerned about readiness. We are trying to field next generation weapons with manufacturing infrastructure designed from a different era. Weapons such as hypersonics, ED, all these different items that are needed in the future wars are just being implemented with old production lines and old equipment and a conventional way of thinking. When requirements change, the factory becomes the pacing item, not the engineering or the design. If we want to outpace threats, we need to outpace our own industrial friction. Low volumes drive high fixed costs and long lead times. Capacity is centralized, it's fragile, and it's really hard to scale. Tooling heavy factories limit change, surge capacity, and sustainment. Labor shortages and sole sources amplify cost and risk. There's a significant reduction in the availability of machinists and welders in the manufacturing of aerospace components, and it goes lower and lower every year. Sustainment dominates cost, but manufacturing cannot respond fast enough. To summarize, gone is the era of leveraging our industrial capacity to backfill our defense needs. We must build our factories to have the agility to adapt, rearm, and forward deploy to the needs of the warfighter. What we're doing at Machina Labs is building around what's called a software defined factory. It's agile in the sense like additive is agile, but with more understandable material properties, leveraging off the shelf formable metal alloys that are not difficult to source like a powder metallurgy that you would find in additive. We take complex design intent and translate it into precision manufacturing through integral steps and parameters. Outcome for customers are mission-ready hardware that's faster, more affordable, with performance gains and designs that conventional processes cannot support. Leveraging machine learning, these systems, called the robo-craftsman, can reduce manufacturing iterations, getting from prototype to production at the speed of relevance. So leveraging integrated deployable manufacturing cell technology, we have the following on-cell capabilities. We can perform what's called roboforming. And roboforming is essentially a term that utilizes called dual-sided incremental forming, where you place sheet metal in the middle of two industrial-sized robots and layer by layer manipulate them to the desired shape. And we can produce shapes that are up to 5 by 15 feet out of alloys such as aluminum, nickel-based alloys, mild steel, even high-temperature alloys like Haynes, Inconel, and niobium C103. Off-robot capabilities include laser welding and integration of complex assemblies. In addition, we also have a capability and a capacity to produce parts and assemblies related to hypersonics, missiles, UAVs, aircraft, and space structures. How we compare to conventional forming using dies and stamping. Traditional sheet metal forming and stamping relies on fixed tooling or dies. That drives a high upfront cost, long lead time, and a serious risk if design requirements change or mission requirements change. Tooling economics are pretty brutal. For aerospace components, it can cost roughly 55 to 100,000, $180,000 for one die or even more, and up to 6 to 12 months of lead time. And then you still have long production cycles and also changeover time. What we do is we're able to form and assemble complete metal structures directly from CAD with no dies and minimal setup in a rapid iteration. Just to kind of put in perspective from one of our customers, They came to us with a design for a development unit used in a missile component. And in 4 months, we were able to produce an integrated assembly of skins with machine components, all laser welded together. And the biggest remark was in our conventional manufacturing company that we're working with, it's taken them 2 years, and I haven't even received a picture of the tool that they're supposed to be using to form these parts. You were able to produce this in 4 months. This is the type of agility we need in order to support our warfighter. So one of the biggest weapon systems that is getting a lot of headlines these days is hypersonics. Open source assessments widely credit China and Russia fielding operational hypersonic systems. The US has faced a program execution and friction, including launcher to missile integration issues that cascade into delays, which prevents us from fielding just one hypersonic system. Test throughput is a bottleneck, ranges and flight corridors are limited, so iteration is slow and expensive. We also hold a stringent engineering standard for accuracy and reliability under extreme thermal loads, which requires exquisite materials such as carbon non-metallic composites to be utilized in a lot of these fuselages. Where we can benefit is a structural manufacturing cycle time using high temperature metal alloy structures with speed and precision without any type of tooling. That accelerates CAD to metal to qualification so programs can iterate faster and move to LRIP without building a single purpose infrastructure. So the biggest problem is this using exquisite materials creates a difficult task of producing a scalable weapons system, while our adversaries are using conventional means. I presented a materials conference last year that focused on hypersonics. To build just a single outside a component, a part of the fuselage, was one every 4 months. If you're looking to scale a new system that's going to compete with our adversaries, that is just not it's not going to go well. So building hypersonics. Being able to leverage our technology, we can focus on three things at once, which is one, using high temperature metallic alloys, using our process of advanced forming and assembly, and a real prototype to production path, we can form all the various parts associated with the fuselage of some of these structures. And this is exactly where tooling heavy factories slow you down, and also leveraging these exquisite materials because every design change punishes you with time. Every design change that you make or every test that you fail, you have to iterate quickly. If you're using dyes, it's going to take you another year to make a new dye. If you're using exquisite materials, you're going to have to develop a new process and new tools to be able to continuously iterate. You just won't be able to sustain that type of development cycle. With our technology, you're able to leverage an iterative process that's rapid. Companies can form most, if not all, of these required components needed for the metallic fuselage. And moving away from these exquisite complex materials reduces the lead time and increases the scalability. In most of these cases, using these highly advanced complex materials is like sending a Ferrari to do a Ford's job. Some of the projects that we're working on, unfortunately, I can't discuss because of restricted customers, but the ones that I can discuss are this one, for instance, which is a low cost hypersonic demonstrator. We're working with Ursa Major to design and manufacture a fuselage for a low cost hypersonic vehicle. Our factory advantage is being able to form and join all of these pieces of the metallic structure with Ursa helping out with testing and design. We can form and join all of these high temp alloys at the speed that we need them. The goal is faster qualification at a lower cost without compromising mission requirements. In addition, we have a project that we're working on with another customer. This is essentially forming and assembling a metal structure that's used for propellant tanks using no dyes and readily available alloys. The goal is straightforward to accelerate this qualification and production for this product that is already being fielded and being able to supply, be a second source contractor for our customer to mitigate any kind of lead time that they're having with their current supplier. We are advancing multiple initiatives with this restricted customer, including a US based Machina factory to support agile, scalable, production ready manufacturing. In addition, we were selected by NASA to manufacture a development COPV or carbon overwrap pressure vessel liner. We essentially were using the technology to form custom-sized hemispheres for metallic liners, which already have a long lead time and are single sourced by our US government. With our technology, we're able to take a lead time that would take years to days. We're able to form one of these domes per day using our technology that can iterate faster and increase the speeds accordingly. That enables optimized volume efficient shapes and lightweight high strength alloy selection without tooling cost or delay. The goal is reduced lead time and maximum storage utilization for spaceflight and satellite missions. This is software-defined manufacturing in practice, where optimized geometries and then off-the-shelf materials, rapid iteration without any type of tool or die needed to form these parts. We're going to take this next step by being able to produce even larger domes for our customer use in space launch vehicles. So now we're talking at least up to, instead of going from 30 inches up to 10 feet in diameter using our roboforming process. So really, the end state is deployable production. We can scale up, switch product lines, and relocate as necessary, even toward the forward deployment areas. It supports aerodev programs. We also have commercial partners like Toyota and alloyed applications. We also operate with a cybersecurity posture that's required, including a CMMC Level 2 compliance certification. The bottom line is Machina factories adapt to changing mission needs and product lines. No longer are you constrained to building one product under one factory. You can build multiple different products under one factory that can support any mission you require. So, as we embark on a new system to support the warfighter and our allies, Machina is proud to be a part of the system that provides our troops with the tools they need when they need it. Thank you very much for your time.